Our topic today, I'll start off the presentation, do a few slides. I'll pass it over to Trevor. He'll get into the nuts and bolts of the architectures we're comparing against, and then I'll finish up with a conclusion. So that's the order of the speaking. We've decided if you have some questions, you can put them in the Q&A sections, and we should have plenty of time at the end to review those questions. So let me start off. The title kind of says it all. We really wanted to get together and talk about operational carbon and energy when we're talking about reclaiming heat from refrigeration systems. And it's important to note that we only say space heating. We didn't include hot water for this study. It's all about reclaiming heat for space heating. So that's what we're talking about. So if you can go to the next slide, please, Trevor. So probably wondering, why we decided to go ahead and do this study. And Henderson and Copeland have a good relationship. We've been working together for a long time on a number of projects. And it kind of came about from a couple of folks. I believe it was Dennis Hagler and Autumn Nicholson originally. Maybe you were involved, Trevor, at the time. Started talking about, opportunities to work together to answer something that we both have been asked a lot. It's, what about heat reclaim and what are the real energy implications of using heat reclaim for space heating, specifically on a CO2 system? And how does that compare to legacy HFC systems? So that's how it came about. So we decided to work together collaboratively with a bunch of folks. I know I'm only mentioned 4 here, but there's a lot of other individuals from both companies that were involved in the development and the number crunching and a lot of areas. So thanks to all of those folks. But we really wanted to create a comprehensive energy and embedded carbon comparison of really common refrigeration systems that are used and space heating architectures. For 2 size of stores, the supermarket store around 60,000 square feet, and then a hypermarket much larger at 190,000 square feet. And I'll go through the specifics in a few minutes. We really wanted to understand how the implementation of heat reclaim can actually further promote the transition to CO2 refrigeration by adding that extra layer of value from an energy and decarbonization. And, when you do that, inevitably it helps to support the industry's significant investment towards natural refrigerants like CO2 because of refrigerant regulations, but also, as many of you know on the line, a lot of retailers have ESG goals. They've already publicly announced they're going to be net zero by 2040 or 2050. And 2040 is only 15 years away. It's 25 years away. But when you've got a lot of properties, there's a lot of work to do in order to get to that net zero. So providing the right information to make decisions today that last 20 years is a big deal. So that was a reason why we did it. So the next slide, please. So we wanted to look at all 3 types of emissions, and the one that's closest to us in the refrigeration that we hear about all the time, of course, are refrigerant leaks. And a real simple one, you got a 2,000-pound CO2, 2,000-pound 404A system that leaks at 20% a year. When you do the math, that's 713 metric tons of carbon emissions only from the 404A. If you change that to CO2, that same amount of 20% on 2,000 pounds ends up being 0.18 metric tons. It's significant reduction. There's no doubt about that. And of course, you've got on-site combustion, so gas burning off produces an emission. The second emission, scope 2, is really about the power required, the emissions from the power generation required to power up that store. So a lot of retailers are also looking at, well, how do I reduce my overall energy. What do I need to do to reduce my overall energy, which automatically reduces my scope 2 emissions? And then the third component there is scope 3 emissions. Now, for our study, because we could only really measure at this point in time leaks due to supply chain of gas going to the store. And so you say that's very limited, because really when you're talking about scope 3, it essentially represents the environmental impact of any business activity that happens beyond the company's direct control. So yes, this gas supply is beyond the company's direct control, but there are other things like the cement that goes in the building, the infrastructure, the steel, any kind of refrigeration equipment inside, and that's a lot harder to get your arms around. So I'm going to talk about an initiative at the end of this presentation that started from a few companies to try to really figure out the overall embedded carbon, which includes everything that maybe that store owner does not have control on, and how does that factor in. So we'll talk a little bit about what's happening there in the future. So the next slide, please. So here's what we studied. I mentioned two sizes of stores, 57,000 square foot supermarket and a 190,000 square foot supermarket. So really two difference, because the refrigeration needs are slightly different in both. They're not always exactly the same from percentage perspective, and I'll bring that up. But we also wanted to look at 6 different climate zones, because we're talking about space heating. So we wanted to look at hot Miami all the way to Minneapolis, where your space heating becomes much greater in Minneapolis than it does in Miami. And then you had some in the middle that were kind of an average. So that was important to understand. And then the 2 architectures, refrigeration architectures we looked at, were distributed 448A scroll packs with enhanced vapor injection. Enhanced vapor injection provides subcooling to the liquid. So that's an advantage. So we wanted to make sure we captured that because it's popular. And then, of course, your CO2 booster systems, but with adiabatic gas cooler. We did not do dry gas cooler because the majority of CO2 systems out there are being installed with adiabatic. So that's what we decided to use as our baseline. And then Trevor will talk about these in more detail, but 3 space heating types with and without heat reclaim from the refrigeration systems were evaluated. So baseline system was no reclaim, standalone gas-fired rooftop units, or water source heat pumps with electric boiler. That was number 1. The other one was reclaiming water, reclaiming heat from water, and water source heat pump with electric boiler. And then the last one was direct air reclaim. So using that CO2 to reclaim heat directly, supplemented with electric resistance heat and or air source heat pump. And as I mentioned, Trevor will go through these in detail. Next slide, please. So for the sake of the study and an energy analysis assumptions, we have to look at the bin hours of operation of all those 6 climate zones, of course, and how many hours do they operate at every temperature in the temperature bins. And we decided to use 55 degrees and below as the point of ambient temperature that required heat if you're below 55. Now you may be sitting there and say, yeah, but my stores need heat at up to 70 or 75 degrees, but we couldn't have a moving target. So we decided 55 was the point where everything below 55, dry bulb ambient required heat, and above did not. So that was our line. The other thing we needed to consider is that we understand that refrigeration loads, as it gets colder outside, the load starts to drop off. And there's a low temp application. So you've got a variable load profile as your ambient, you can see on the x-axis of the chart on the right. As your ambient gets colder, the dark blue line represents low temperature applications, they kind of bottom out at 80 degrees of full load, 80% of full load when we reach 40 ambient or lower. But the medium temp starts to fall off around 75, and it goes a little bit below 70% of full load for medium temp when you're at 40 and below. So the reason we had to do that is because it's more real life, number one, and because we're using free heat or condensing heat in order to provide space heating, that amount of space heating starts going down. The availability of heat goes down, of course, as your load decreases in the winter. So we needed to factor that in. Next slide, please. So let's take a look at the architectures we're comparing. I mentioned 57,000 square feet supermarket and 190,000 square feet. We've got a 448 system on the left. You can see you've got some scrolls, small scrolls. You've got that purple line is my enhanced vapor injection line. And you've got a plate heat exchanger, which is providing subcooling. There should be a little expansion valve in this liquid line prior to the plate heat exchanger. So imagine that it's there, and the vapor coming off the heat exchanger goes into the scroll. So that's basically that subcooling effect. The system on the right is our CO2 system. It's a basic system other than the fact that we've got adiabatic gas cooler. And the assumptions we made at the bottom of the table is 448A medium temp at its 15-degree TD on the condenser for medium temp, a 10-degree TD for low temp. And you can see the minimum saturated condensing temperatures for low temp at 65, medium temp at 70. Our liquid temperatures, or minimum liquid temperatures trying to maintain them year round. And then the booster had a 13-degree subcritical TD and around 7, it's not shown there, but when it's operating supercritical, with a minimum saturated condensing of 60, 5-degree subcooling when we are in subcooling mode, with a 36-degree flash tank, which is about 520-pound liquid line pressure, flash tank pressure. So when you look at capacity, we're looking at 4 systems for the supermarket, 448A, and 1 centralized system for CO2. Low temp loads, 258.7 thousand BTUs, and around 274,000 BTUs medium temp. That's for the supermarket. When you look at the hypermarket, we've got more systems because it's a larger capacity, 6 distributed scroll packs, and 3 CO2 units to provide the capacity. And you can see, though, what's interesting is the low temp load is only marginally higher on the hypermarket than it is on the supermarket, but the medium temp loads are much higher. That's typically how they're set up. Now, observations. We really didn't inspect it, but what's interesting is the supermarket, the percentage of low temp loads is greater for the supermarket at 35% versus hypermarket, which is lower. And what happens there is because your supermarket has higher low temp percentage of total load, that means that when you look at your CO2 system, your medium temp compressors have to do more boosting. They've got an extra 6% more capacity to boost up. And I'll come back to that because it has an impact on efficiency when you compare one supermarket to hypermarket. So the other observation we saw is that, of course, CO2 has an efficiency advantage, particularly in low ambient. And so the areas that have more low ambient hours of operation tends to do better. And then the last observation here that we've listed out talks about the adiabatic gas cooling, which I already mentioned, provides high ambient mitigation, so energy efficiency gains versus a dry gas cooler. And that changes dramatically based on how dry your regions are. But that was part of our study. So the next slide talks about adiabatic gas cooler and really how much moisture, how much water we're using. We know that they are common, so that's why we chose them. We also understand that we're using, of course, water, which is natural resource, which you have to take into account, and the temperature that the water gets turned on is 72, greater than 72 degrees. So at greater than 72 degrees, our water on, and of course, when we go below 73 degrees, water turns off. And what we tried to do here in this table is to give you like a snapshot on how much water is really used, because it is a natural resource. So there's a cost associated to water flow. There's also a cost associated with drainage. In Los Angeles, you can see a runtime in supercritical is 0%, because anytime it is over 72 degrees, which is 5% of the time in wet mode, that's really the wet mode keeps it from going transcritical. And you see all the hours of operation and the percentage of transcritical runtime. And to the far right, you see the amount of thousands of gallons per year. So Los Angeles, for example, in a supermarket, 45,000 gallons in a year of water use for 5% of the year. Whereas Miami on a supermarket, it's 400,000 gallons a year. And then little gray table here, according to the EPA, an average American household uses about 30,000 gallons of water per person. So if you had four people in a family, 120,000 gallons. So it kind of gives you an idea of how much water is being used relative to this particular chart compared to a home of 4 people. Next slide, please. So energy results that do not include heat reclaim. Supermarket annual energy refrigeration energy use. Now, if you take a look at the table here, the y-axis is annual energy in megawatt hours, and we have the cities we chose at the bottom. The black bar is 448 with EVI, that's our baseline, and CO2 with adiabatic gas cooling. And you can see that in most of the cases, CO2 is marginally better, except for Los Angeles, it's slightly higher, and Miami is slightly higher. There's more hours of operation, bin hours, in the warm ambient areas than the other cities. So that's supermarket, 57,000 square feet with 35% of the low temp load to total. Now, if we go to the next one, which is hypermarket, you'll see that the bars look quite different. The hypermarket is about 3 to 20% lower for CO2 energy. And you can see Minneapolis, Chicago, Dallas, they're all lower. Miami, just marginally lower. Again, this does not include heat reclaim. And if you click the next build, please, Trevor, it's all about that difference in percentage of low temp to total load. The supermarkets was higher, as I mentioned, 35%. The hypermarket was a little bit lower. And you may ask yourself, well, why didn't you use the exact same percentage? We didn't, because the hypermarkets typically have a lot more medium temp to low temp load. So we wanted to try to stay with real life refrigeration schedules. Okay. Next slide, please. So this is where I'm going to pass it off to Trevor, and he'll go through the different architectures and what they look like from a heating perspective.
So the space heating systems and assumptions. So our baseline strategy was no reclaim and simple gas-fired heating units on the rooftop units is typically standard. So we're looking at return air of about 67 degrees, a minimum supply air temperature of 85 degrees for the heating side. And we tried to maintain the minimum heating set point at 85 degrees supply air temperature throughout. So that'll be the same for the water source heat pump. And then as we start getting into the heat reclaim. So with the water source heat pump system, again, baseline was no reclaim. The water source heat pump system, you typically have a boiler pump, fluid cooler, moving heat around within a loop. And then the water source heat pump pulls heat out of the loop or ejects heat into the loop, depending on whether it's in heating or cooling. And the typical heating coefficient of performance is 4 for the temperatures that we were looking at for the water source heat pump systems. So when we start getting into heat reclaim with the water source heat pump system, there's a heat exchanger on the compressor outlet, and that our loop feeds through that heat exchanger and allows us to basically shut off the boiler during certain periods of time if we have enough heat to meet the building's load. So the other system that we looked at for heat reclaim was a direct air system, where we are running compressor gas to a heat reclaim coil in the rooftop unit. So there's a diverting valve after the compressors, sending hot gas from the compressors directly to a heating coil, and then it returns from the heating coil as a either mixed desuperheated gas or as a liquid downstream of the gas cooler condenser. And again, we're looking at a minimum supply air temperature of 85 degrees. We looked at, for supplemental heat, we looked at electric resistance heat. We also looked at air source heat pumps as an additional option for reducing carbon and reducing gas usage. Air source heat pumps have a better coefficient of performance because they're pulling heat out of the atmosphere. They work much better in warmer climates than they do in, say, Minneapolis, but there's still a significant amount of time, even in cold climates, where you can get a fair amount of heat through an air source heat pump. And we're listing out the average COP that we were using for each location. So how does the climate zones impact our heating loads? And how much heat did we have available from each of the refrigeration technologies? Looking at it, here we have heating loads from -10 to 20 degrees for both the supermarket and the hypermarket. No surprise, it's a much higher heating load when it's really cold out, as opposed to when it's only moderate temperatures. Also, the hypermarket has a significantly larger heating load, where the supermarket around 20 degrees, the amount of heat that is available from the refrigeration system is really close to the heating load. With the hypermarket, we're only at best half at 20 degrees. So 20 degrees was the break-even point for the supermarket. Much higher temperatures were needed at the hypermarket. That was into about the low 40s before the hypermarket was coming close. This is a complicated graph showing the annual energy usage for both heat reclaim and so heating and refrigeration for the cities. The cities are listed along the bottom, and then the megawatt hours or equivalent megawatt hours are listed on the y-axis. And the colors denote the options there. So the first two on each are where we have no reclaim used. And so you're paying for all of your heat and all of your refrigeration energy here. So significant energy penalty compared to the use of heat reclaim for the supermarket. So we also, when we looked at it, we noticed that the water source heat pump was even a little worse than the standard natural gas rooftop unit. And some of that is the penalties inherent in the water source heat pump system as you start moving heat from a source production and then pulling it through the water source heat pump. So our gray mixed line there is the gas-fired RTU. So when we started looking at the heat reclaim, direct heat reclaim supplemented by electric resistance heating, in both cases, for both refrigeration technologies, was worse than the water source heat pump. So when we started looking at the water source heat pump, because in many climates, 20 degrees was kind of the break-even point, the water source heat pump could pull all of the heat out very efficiently, and needed less additional heat. So when we started looking at direct reclaim with air source heat pumps, that's when we see a very slight advantage compared to the water source heat pump systems, because we have a larger source with the air source heat pumps to pull heat from the outdoors into the space. So when we looked at the space heating energy results for the hypermarket, it got a little bit different because of the additional heat energy required, because the refrigeration was so much less than what the space needed. So again, the first two bars are no reclaim option. And again, there's a significant energy penalty for not reclaiming the heat. Here we see no real significant difference between water source heat pump or direct reclaim using only resistance heat for supplemental heating in the colder climates, especially. And that's due to the amount of additional heat that needed to be input into the loop and those very cold climates, where we see the real benefit is in more moderate climates in their heating zones, Dallas and Portland. They don't get as cold as Chicago and Minneapolis, so they spend more time in that 25 to 40 degree zone, where that's where you're doing much better on your heat reclaim with the water source heat pump system on the hypermarket. But when we looked at direct air source heat pumps with heat reclaim, that was actually the lowest total energy usage across all the climates, just because we were pulling so much, we had a larger source and better efficiencies. And because the air source heat pump efficiency goes up as the temperature is more moderate, we end up with it being even better in places like Dallas, Los Angeles, and Oregon. So kind of looking at direct air reclaim as complementing air source heat pumps. When we started looking at it, air source heat pumps, you can get some of them to go all the way down to about -15, but you're not getting a lot of energy heat from just the air source heat pump at that point. You're looking more at electric resistance heating. But at the very cold temperatures, when you're doing direct reclaim, you end up getting more of the heat more easily, where the temperature of the refrigerant is enough that you're boosting your outside air. Typically, that is the biggest portion of the load through the air handlers, the rooftop units, typically. So bringing that up to temperature is easier when it's really cold with the direct reclaim. So, and as our reclaim kind of falls off as the air becomes warmer, we see that air source heat pumps cover more and more of the load. So one does incrementally increasing the pressure save operational carbon? So does elevating the head pressure always save energy on CO2 systems? Some of that actually, it kind of depends on the system. So with TCO2 systems, you can boost your pressures into the transcritical region, and that allows you to pull a lot of heat off of them fairly easily. The downside to that is it requires a lot of additional refrigeration energy to get that pressure boost. So instead of going at the minimum, you have a significant energy investment to reclaim all of that energy at a high quality of heat, so higher temperature. So when we looked at it, it got into, you had to be careful about how the system would be run, and you wanted to be able to use all of the heat that the system would produce for the lowest energy investment in your refrigeration system. So one thing is there's not really a one balance point that will work for all systems. With warmer climates and space heating systems being very a small portion of the site energy use, it may not be where you need full reclaim, or that may be additional complications in your system versus a very cold climate where you're going to want to pull as much heat into building is possible. So when we looked at the Minneapolis hypermarket, trying to see what strategies would yield the best energy results, the water source heat pump reclaim with TCO2. When we pushed the water source heat pump system into transcritical, we actually saw a very slight energy penalty. We could reclaim a little bit more heat, but we needed a lot more refrigeration energy. So when we looked at the direct air reclaim strategy, that is where we saw a benefit to raising our pressures. We looked at raising it above the absolute minimum and then all the way into a transcritical point. And what we saw was a very slight advantage going just a little way up and not into transcritical. Some of that was based on kind of our system architecture that we were looking at. We were looking at a lot of outside air being brought in directly over a coil. And there, you don't need to have it as hot to pull all of the energy out that you can. So when we then added the air source heat pump versus the electric resistance, then we saw a marked decrease in the total energy use. And that is directly related to the higher COP of the air source heat pump versus electric resistance heat. So the operational carbon assumptions, when we were looking at the scope 1, 2, and 3, so the HFC system was R448A with a GWP of 1,387 versus R744 GWP of 1. We assumed a consistent leak rate between the two of 25%. So for the natural gas, it was combustions on site and supply chain leakage. And scope 2 was indirect emissions for basically emissions based on how dirty the power grid is for the area we looked at. And that all those bundled together is the carbon footprint. So here we have a graph by city on the y-axis, and the x-axis is total emissions in metric tons of CO2 equivalent. So the colors here represent where those different emissions are coming from. Blue is the refrigeration energy. Yellow is the gas heat. The hatched green is direct refrigerant impact, and then red or orange is space electric heating energy. So looking at this, the first in all of these, we did the R404A no reclaim gas option. Then we did the R448A water source heat pump reclaim option. Then we did the CO2 water source heat pump reclaim option, and then the CO2 direct air reclaim with air source heat pump. So looking at the supermarket here, we have significant reductions from the baseline strategy to our best case. It's 2 to 3 times the carbon emissions. So air source or heat or R44 or sorry, TCO2 with heat reclaim, between the 2 heat reclaim options we're looking at is very similar in total carbon across for each of the climates. When we looking at Los Angeles and Miami, where we have very low heating, we looked at just desuperheating only. This is probably going to be a more common strategy in those very warm climates to not fully condense your refrigerant. It does allow for a simpler system on the air side if this is used. Does have it's not quite as good as the water source heat pump. In those regards, slightly more energy, but it is a much simpler system. It's also desuperheating would lend itself to something like dehumidification reheat for comfort cooling process. We didn't include that as part of the study, but it is a possible use case. So when we looked at the hypermarket operational carbon, again, we see the air source heat pump. Here, the air source heat pump outperforms the water source heat pump with reclaim, and that's due to the additional energy we're spending in electric heat throughout the year. At the very coldest points, the amount of electric heat is actually going to be the same for those very cold hours. It's just that the air source heat pump has much better efficiency in the more moderate temperatures. So our baseline for the hypermarket compared to our best case is roughly 4 times the operational carbon compared to air source heat pump with direct reclaim. So conclusions, future considerations. Heat reclaim definitely saves heating energy significant amounts in the very colder climates and reduces carbon footprint. Looking at air source heat pumps paired with direct reclaim, it gets to be very viable even in the colder climates. Increasing our refrigeration discharge pressure for higher quality heat has trade-offs for total building efficiency. And this is one area where the engineers are going to have to look at what those trade-offs are to define the optimal balance point for facilities, HVAC, and refrigeration solutions. So, and then there's total cost of ownership and feasibility when you're looking at transitioning existing buildings to meet decarbonization targets. Things like adding heat reclaim if a building doesn't have it, or go to air source heat pumps during retrofit applications from old gas-fired units.
So if any of you are interested in basically reading the white paper, so we wrote a white paper, Henderson Engineers and Copeland, and it's exactly the same title as a topic that we had today. You can scan that QR code that's on your screen right now, or you can wait for a PDF, a copy of the presentation to come to you that will be available. Well, that's one thing. The other thing I wanted to point out, I mentioned earlier on that that Scope 3 emissions is difficult to wrap our arms around. There's no one set methodology in the refrigeration space yet. And there's a company, there's an association here called Chartered Institution of Building Services Engineered. And they've developed a, it's called CIBSE TM65. It's an internationally applicable methodology for calculating embodied carbon in building services engineering. So that exists to try to identify all those pieces of the embodied carbon in a commercial building today. And there's an act there. There's a group, them, along with Amazon and Effectera, are interested in developing a TM65 methodology for refrigeration. And as a group, they'd like to be able to develop a draft document by the end of 2025. And they've reached out to Copeland and Henderson Engineers. And if anybody else is interested in learning more about that, please reach out to Trevor or myself, and we can organize the meetings with the right folks to start having those conversations and maybe get to that refrigeration methodology of Scope 3, understanding Scope 3 better for our space. So thank you very much. I appreciate it.